Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's presentation on Poisson distribution part 4. In the last session, we have solved some problems on Poisson distribution, and again we will continue the same in today's presentation also. Some other problems on Poisson distribution and new concept to fit a Poisson distribution. This concept has been introduced in the case of binomial distribution also. The same concept we will repeat here, and we fit a Poisson distribution. Now coming to the first problem, if two cards are drawn from a pack of 52 cards which are diamonds, using Poisson distribution, find the probability of getting two diamonds at least 3 times in 51 consecutive trials of two cards drawing each time. So again I repeat, if two cards are drawn from a pack of 52 cards and those two cards are diamonds, so first we need to find the probability of drawing two diamond cards from a pack of 52 cards, and then find the probability of getting two diamonds at least 3 times in 51 consecutive trials. So that means the number of trials n is given 51 and probability of success p is the probability of drawing two diamond cards. So in a pack of 52 cards, we know that there are two colors, red and black, and in each color there are two types. So here hearts and diamonds, in black clubs and spades. In each type there will be 13 cards starting from S, 2, 3, 4 and so on, 10, J, Q, K. And here two cards are drawn from a pack of 52 cards. So in how many ways two cards can be drawn from a pack of 52 cards? Out of n objects, we are selecting R objects in NCR ways. So two cards can be drawn from 52 in 52C2 ways. This is the total number of cases, 52C2, and those two cards must be diamonds. And how many diamonds are there out of 52 cards? In each type there will be 13 cards. So there are 13 diamonds, and these two cards must come from those 13 cards itself. So n of E, therefore n of E is 13C2, and therefore the probability of drawing two diamond cards is 13C2 by 52C2. 13C2 by 52. So therefore the probability of drawing two diamond cards is given by n of E by n of S, which is 13C2 by 52C2. If you find this value using NCR, n factorial by r factorial and n minus r factorial, we will get the answer as 3 by 51. Now out of 51 trials, at least getting two diamonds at least 3 times, So x equal to 3. This should happen at least 3 times out of 51 trials. So therefore by Poisson distribution, lambda is NP. So lambda equal to n into probability of success P. So 51 into 3 by 51. So which is the value of lambda equal to 3. Now use the Poisson distribution formula. Probability of x successes is e power minus lambda power x by x factorial, and here probability of x successes is lambda is 3, e power minus 3 by 3 power x by 3 factorial. And in this problem we need to calculate getting at least 3 times. So, it is required to find probability of at least 3 times. So, x less than or equal to, that means x greater than or equal to 3. Probability of x greater than or equal to 3. So, minimum is 3 or more than 3 times also. So, which can be calculated using probability of x less than 3. So, 1 minus probability of x less than 3 means x equal to 0 plus x equal to 1 plus probability of x equal to 2. 1 minus sum of these 3 gives the final answer. So, after calculating these values, here x equal to 0 means e power minus 3. So, here lambda is equal to 3, e power minus 3, 3 power x by x factorial. So, e power minus 3, 3 power 0 by 0 factorial, e power minus 3, 3 by 1 factorial, e power minus 3, 3 square by 2 factorial. So, 1 minus e power minus 3 into 1 plus 3 plus, so 3 square is 9 by 2. So, after simplifying this, we will get 0.57681. So, the probability of getting at least 3 times out of 51 trials, getting 2 diamond cards is 0.57681. Now, the second problem, prove that 3 successive values of Poisson variate cannot have equal probability of success. Prove that 3 consecutive values of a Poisson variate, that means if I consider x, x plus 1, x minus 1 consecutive values, the present value, previous value and the next value, cannot have equal probability of success. So, that we need to prove. Now, let x minus 1, x and x plus 1 be 3 consecutive values or successive values of a Poisson distribution. So, x minus 1, x and x plus 1. Now, suppose using recurrence relation of Poisson distribution, probability of x plus 1 successes is lambda by x plus 1 into probability of x successes, and we have to prove that cannot have equal probability of success. So, let us prove this using the method of contradiction. Method of contradiction, what is that? Here we have to prove that these 3 values are not the same. The probability of successes are not the same. We start with an assumption that these 3 probabilities are equal. So, let us suppose or let us assume or suppose probability of x minus 1 successes is equal to probability of x successes is equal to probability of x plus 1 successes. This is our assumption, just as an assumption. So, using the recurrence relation, probability of x successes is given by lambda by x into probability of x minus 1 successes. So, from this, probability of x minus 1 is equal to x by lambda into probability of x. This is probability of x minus 1, and here this is our assumption, equation 1. Let us suppose our assumption is equation 1. Now, this 1 implies probability of x minus 1 is equal to probability of x is equal to probability of x plus 1. And just now we have calculated probability of x minus 1 as x by lambda probability of x is equal to what is probability of x plus 1 from this relation, recurrence relation, lambda by x plus 1 into probability of x. So, we have this relation, x by lambda p of x is equal to p of x equal to lambda by x plus 1 into p of x. So that implies if you consider these two, x by lambda is equal to 1 because p of x gets cancelled. So x equal to lambda, that is the value of lambda is x. Next, if you consider these two, then lambda by x plus 1 equal to, if you consider these two, then lambda by x plus 1 is equal to 1. That implies lambda is x plus 1. But what is lambda here? Here lambda is the mean of Poisson distribution. The mean of Poisson distribution, which is unique. How can we get two different values? Which is a contradiction to the fact that mu equal to lambda is unique. Why we reached this contradiction? Since, so our assumption that all these are having same probabilities is wrong. So that implies our assumption that p of x equal to p of x minus 1 equal to p of x plus 1 is wrong. Hence, the three consecutive values probabilities are not the same. The probability of number of successes, x successes, x minus 1 successes, x plus 1 success, these are not equal. Now coming to the third problem, the condition is given 3 times of probability of x equal to 4 is equal to half into probability of x equal to 2 plus x equal to 0. And what is the formula in Poisson distribution? In Poisson distribution, the formula is e power minus lambda, lambda power x by x factorial. So 3 into probability of 4 times success, e power minus 4 power x by x factorial is equal to half into e power minus 4. Here lambda is unknown. We need to calculate the value of lambda. So let us use this formula here. 3 times probability of 4 successes, e power minus lambda, lambda power 4 by 4 factorial is half into e power minus lambda, lambda square by 2 factorial plus e power minus lambda into lambda power 0 by 0 factorial. So here 3 times of e power minus lambda, lambda power 4 by 24 is e power minus lambda is common. So lambda square by 4 plus 1. So these two gets cancelled, and here we will get a polynomial equation in terms of lambda. By simplifying, we will get this 4th degree polynomial equation. By simplifying, we will get this 4th degree polynomial equation, and by solving this, we will get the values of lambda as lambda equal to 2. So therefore, the probability of x successes is e power minus 2 power x by x factorial. And now we have to calculate the second problem, probability of x less than or equal to 2. Here the mean of the distribution is lambda, that is calculated here, and now probability of x less than or equal to 2. So the probability of x less than or equal to 2 is probability of x equal to 0 plus probability of x equal to 1 plus probability of x equal to 2. So which is e power minus 2 power 0 by 0 factorial plus e power minus 2 by 1 factorial, e power minus 2 square by 2 factorial. So e power minus 2 is common, here we get 1 plus 2 plus 4 divided by 2. So this is 5 e power minus 2, and the answer is 0.498. Now coming to the next problem, fit a Poisson distribution to the following data. Already we have discussed this in the previous concept, binomial distribution. To fit a particular theoretical distribution, here theoretical distribution of a given frequency distribution, here x values and corresponding frequencies are given. We have to find the corresponding probabilities and then multiply each probability with total frequency, that gives the expected frequencies, EIs. These are observed frequencies and these are expected frequencies. So to fit a Poisson distribution. Here we calculate these probabilities using Poisson distribution formula. What is that? Probability of x successes is e power minus lambda, lambda power x by x factorial. So first we need to find lambda. What is lambda? Here lambda is the mean of Poisson distribution. So for the given frequency distribution table, the mean of given frequency distribution table is given by sigma xi into fi by sigma fi, where sigma fi is the total frequency. Here by adding all these, sigma fi is given by sigma fi is 200, and so this value will be 122 by 200, which is equal to 0.61. So the mean of the distribution is 0.61. We know that the mean of Poisson distribution is mu equal to lambda, which is equal to 0.61. So we have the formula to find probabilities of x successes, e power minus lambda, lambda power x by x factorial, which is equal to e power minus lambda, lambda power x by x factorial, which is equal to e power minus 0.61 power x by x factorial for x equal to given 0, 1, 2, 3, 4. So we need to calculate all these 5 probabilities. So probability of x equal to 0, x equal to 1, and x equal to 2, then 3 and 4. Just substitute the value of x equal to 0, 1, 2, 3, 4. We will get the answers as e power minus 0.61 into 0.61 power 0 by 0 factorial, and similarly we can continue, and by multiplying with total frequency we get the first expected frequency E naught, then multiplied by this. So these values can be obtained by substituting x equal to 0, 1, 2, 3 and 4. So you can calculate these probabilities, then multiply with the total frequency. What is the total frequency here? N equal 200. So then we will get the expected frequencies as in the first case E naught is 109, E1 is 66, E2 is 20, E3 is 4, E4 is 1. So like this we calculate the expected frequencies. First we find the probabilities, then multiply with total frequency. Hence finally we construct the table x values, given observed frequencies, then expected frequencies. X values 0, 1, 2, 3 and then 4, and given values are 109, 65, 22, 3 and 1. In the problem these values are given, that is why these are observed frequencies. Now we have calculated expected frequencies 109, 66, 24, 1. So this is the Poisson distribution. So using Poisson distribution, first we calculate the probabilities, then the expected frequencies. Like this we can fit a Poisson distribution to the given frequency distribution table. Similarly, there are some problems for practice. Fit a Poisson distribution to the following data. Here in the first problem, total 6 values are given, and the total frequency capital N can be calculated by adding all these values. Similarly, here also you can first calculate N, then first find the mean of the frequency distribution table using sigma xi fi by sigma fi. So sigma xi fi by N, and this value is equal to lambda. If you have lambda, use the probability formula e power minus lambda, lambda power x by x factorial for different values 0 to 0, 1, 2 and so on. Then multiply each probability with total frequency, which gives the expected frequency. So these problems are given to the students for practice. In today's session, we have discussed some problems on Poisson distribution and also how to fit a Poisson distribution. And in the next session, we'll discuss about the normal distribution, which is a continuous distribution. Here, binomial and Poisson are discrete probability distributions, whereas normal distribution is a continuous probability distribution. So, we will discuss about normal distribution in the next session. Thank you very much, and we will meet in the next session.